2.1 kind of looked at the limit process behind derivatives, right? That's what it did. And it established where we're going with what's happening next. In particular, the lesson today. So these are basic derivative rules. They're going to be your friend. You will memorize them very quickly because they work the same way every single time. They're very repetitive. It's almost like learning your multiplication tables every single time. 3 times 4 is 12, right? You see it every single time. Eventually you get it because you've done it enough times, okay? So the first 3 we're going to take a look at are ones we have seen graphs for, at least in some form. The first one is a constant graph. So if you have a constant graph, it looks like this. It's a horizontal line. What's the slope of a horizontal line? 0. Therefore, the derivative, which is the slope of the tangent line, is 0. Okay, any constant, any number, its derivative is 0. The second one, power rule, might be the only thing that my husband remembers from his point in calculus. And he took Calc 1 twice because he liked it so much. Not really. This might be the only thing he remembers from calculus. The power rule. The power rule talks about anything to a power n, and n can be any number. So it can be positive, it can be negative, it can be fractions, it can be decimals, it can be radicals. Doesn't matter. And it works the same way. The derivative for a power rule is nx to the n minus 1. So you have this feeling of taking the exponent down in front and then decreasing the exponent by 1. The constant multiplier rule is very much like when we did limits. It's what you would expect to happen. When you have c times a function, and you take the derivative, you end up with c times the derivative of the function. So constant multipliers just come along for the ride. Okay, constants that are added, number 1, become 0. Constants that are multiplied stay. They don't become 0. I think we have a couple more. Okay, 2.5, again, much like 2.4, is just what you would want it to be. When you have a sum or a difference of functions and you take their derivative, it's just the derivative of each of the individual pieces with whatever sign was between them still between them. It's just what you want to have happen. I'm going to ruin your world in a couple of days because it's not going to work that way all the time for everything. But it does for constant multipliers and for sum and difference. Okay? The last ones, sine and cosine rules. Sine and cosine rules are very friendly. They oscillate. Sine turns to cosine, cosine turns to sine with one variation. So the derivative of sine is cosine, and then the derivative of cosine is negative sine. And this is it. These are our basic derivatives. Now, do you remember we talked about, it's still like a week away, it's next Wednesday, a gateway, something called a gateway. The gateway, sometimes I call it a basic skills quiz, is simply derivatives. Okay, it won't just be these rules because we're going to add on rules over the next couple of class periods as well. But it's going to be utilizing these rules along with others over and over and over again because they're so important and crucial to calculus. It's like the multiplication tests that I mentioned before that my 3rd grader is about to start taking in school, right? You do those time tests. Well, yours isn't timed, but they want to do them so many times that she never forgets that 3 times 4 is 12, right? That's the goal. I want you to do these rules so many times that you never forget, at least during your time in calculus, that when you take the derivative of x cubed, you pull the 3 down in front and you make the 3 a 2. I want you to remember that for always because they're going to keep coming up over and over and over again throughout the time you're in calculus. It's really important, okay? Cornerstone kind of stuff. So when we take a look at these examples, we're going to apply these rules, and sometimes there's some cleanup and sometimes there's not. When we're working on our homework, when we're working on quizzes, exams, you're going to have cleanup. When you do your basic skills quiz, your gateway that we're talking about, you don't have to clean anything up. So I'll show you where you can stop if you were stopping on a gateway, and I'll show you where you have to get to if we're doing homework and so forth after that, okay? So our first one is y equals x to the 7th. Okay, so what am I going to do the derivative of this? First of all, the notation was that prime notation. We talked about that last time. What's the derivative of x to the 7th? 7x to the 6th. That's the power rule. The 7 comes down in front, and I decrease the exponent by 1. Is that okay? Awesome. Okay, the next one has pi in it. Pi is a number, so the number in front is a constant multiplier. It means it comes along for the ride. Does not change. But the derivative of cosine is what? It's negative sign. So you can write it like this, and if you were doing your gateway, you could leave it like that. That's just silly to leave it that way for us, really looking at it. And maybe you thought it was silly to write it that way to begin with. You can definitely and should definitely put the negative in front, either from the get-go or at the end. Okay, any questions so far? All right. Now, these two were very nicely written in forms that looked just like the ones that I gave you the rules for, right? You saw a cosine. You saw an x to the 7th. Very clean. But they're not always. Sometimes they're written in a form that doesn't quite look like what we've had, but I promise you everything in this section is able to be manipulated to be in the form we want. So here's an example of one that doesn't quite look like what I was given to begin with. There is an x squared, but the problem is it's in the denominator, and there was nothing in any of the rules that I gave you about denominators. We'll have something about denominators later, but we don't need this at this point. We want to be able to rewrite this so that instead of the x squared being in the denominator, it is in the numerator or outside of being in the denominator, if you think about it that way. So the first thing to be reminded of is that the constants do not move. This is still 4/3. 3 is in the denominator, it doesn't get to move anywhere. 4 is in the numerator, it doesn't get to move anywhere. The 4 and the 3 are stuck. But the x with the exponent is movable. If I move the x up to the numerator, how can I change the exponent to make it equal? Yeah, I can write it as x to the negative 2. And you can write it like that, or you can actually bundle it up with the 4 in the numerator if you wish. It doesn't matter. Kind of like writing it separate, so I'm going to leave mine separate. This is how we can rewrite it. Once you've rewritten it, then you're going to differentiate. Differentiate means find the derivative. So we have our constant multiplier rule. That's the 4/3. And then what am I going to do with x to the negative 2? Okay, I'm going to multiply by the negative 2. And what will my new exponent be? Negative 3. Okay? So it kind of looks like the exponent got bigger, but that's because we're dealing with negatives, right? Negative 2 minus 1 would be negative 3. Now, if you were doing a gateway, you can stop here on a gateway. The point of the gateway is not for me to test your skills of algebra manipulation. I'm trying to isolate the calculus components we're working on. So you can stop very quickly on a gateway. But the reality is that math intermingles, and those algebra skills are important, and you should be able to clean this up at the end. So when we're working homework, we're working quizzes, we're working tests, we're going to keep going one more step, and we're going to clean that up. So what do I mean by clean that up? Well, I mean the exponent started out on the bottom, so we want to put the exponent on, not the exponent, but the variable with the exponent on the bottom. So, and I also have this 4/3 and negative 2, and those should be able to be multiplied pretty easily. So we're going to do that as well. So we'll start with the values that are being multiplied. What is 4/3 times negative 2? Yeah, negative 8/3. You can put the negative on top or the negative in front. It doesn't matter. And then my x to the negative 3 will move back into the denominator and become what?
Just x cubed.
Yeah, just x cubed. So the final result of all of the algebra manipulation looks like negative 8 over 3x cubed. Okay, is that all right? Okay, so we're going to look at another one where it doesn't quite look like what we've started with in terms of our rules. So we're finding the derivative, g of x. It's x cubed minus 3x squared plus 4 over x squared. And there will be another rule that we can do this with later, but we can also do it with the rules we already have. So as we're taking a look at this, I want to remind you of a property of fractions that we don't use this way very often, but it says that this is equal to dividing each of the individual pieces by the denominator. Whoops, that's supposed to be a 2. That's correct, right? Now, you might not have looked at that and thought, hey, I can do this. But you can. You can separate each individual piece over the entire denominator. And our entire denominator is x squared, which is a pretty closed, concise form. If the denominator had a subtraction or addition in it, it's messier, and we probably wouldn't want to do it this way at all. And we'll have another rule for that. But because our denominator is simply x squared, this works very well. I can clean this up a bit. So the first piece, what's x cubed over x squared? X. What is negative 3x squared over x squared? Negative 3. And while the last one doesn't simplify, right, like I don't get to divide any x's out, I can do exactly what I did over on this problem, yeah? I can rewrite it in a form that's more user-friendly. So I can write it as 4x to the negative 2. Is that okay? Okay, does everybody understand that we didn't do any calculus yet? All of that was algebra. Maybe a long time ago algebra, but it's all algebra. So the algebra starts at the beginning of this particular problem. Now we're ready for our derivative. So what's the derivative of x? 1. So those of you who have not had a bit of calculus, a reminder here, the x at the beginning means it's 1 times x. I didn't have a rule actually written out about this, but what is the derivative? That is, what is the slope of the equation of y equal x? Well, it's 1, right? So the coefficient, if you want to add it to your list, it might be helpful as you're thinking about this to remind yourself. So if you have, we'll call it g of x equals, we'll just do mx plus b. Then the derivative for this is just m, because it's the slope of the tangent line. You can do that with pre-calc. The slope of a tangent line is the slope of the actual line, so it's m. Okay. What's the derivative of the negative 3 part? That's 0. So the derivative of any constant is 0. You don't necessarily have to write the 0 in. I'm going to for this time anyway, just to make sure that when you look back at it later, you realize what happened. And then the next piece, 4x to the negative 2, is just like the last problem. Now, if you wish, you can write down 4, and you can write down the negative 2, and you can write down x to the negative 3. That's fine. But you can also probably do this in your head, on this one especially. What I'm going to do is I'm going to take this and I'm going to multiply it. So I've got 4 times negative 2. And 4 times negative 2 is negative 8. So you can probably skip that piece, especially when the numbers are simple like that, and just do the multiplication in real time. But then the exponent for x will be negative 3. Allie?
Where'd you get
The 0 is the derivative of negative 3. Derivatives of constants are 0. Yep. Any other questions? So this is a good gateway answer. You just stop right there in the gateway. We don't go any further. But again, for the purposes of cleaning things up, we will go further in any other avenue. The 1 can stay. I do not need to keep writing the plus 0, right? And this will be negative 8 over x cubed. If you were checking something, like I know some of you probably use some online resources sometimes to check your answers, or maybe if you're struggling, or if WebAssign kicks it back out and doesn't like this, what it might do is get a common denominator. That's a possibility here as well, since the original problem started out with a common denominator. It could do that, and so it actually might do this as x cubed minus 8 over x cubed. By getting into common denominator, that's a possibility. Can everybody see how that would happen? Okay, it's not any better of an answer at all. Neither one is bad. It's just another version of it. So just so that you're aware. Okay, radicals. I didn't give you anything about radicals, But there are some pieces of information about radicals that allow us to turn it into exponential form. So let me remind you. If you have, actually we'll do it this way, the nth root of x to the m, this can be rewritten in radical form as x to the m over n. So m stays the exponent, and the nth root, the index of the radical, becomes the denominator of the exponent. Okay, again, that's an algebra topic. It's not one we use a lot, though. But we can use that when we're working with our radicals to rewrite them and then to use our exponential rules, that power rule specifically. So the first thing I'm going to do is I'm going to rewrite cube root of x. Well, it doesn't look like it has an exponent, so its exponent is understood to be 1. So this is x to the 1/3. So how would I rewrite the 5th root of x? X to the 1/5. Okay, is that all right? We have to be able to do the rewriting or we're not going to be able to do the derivatives. Okay, so at this point we're ready to do the derivative. So x to the 1/3 means I bring the 1/3 down. And then I decrease my exponent by 1. So what is 1/3 minus 1? Negative 2/3. And I'll just tell you this right now, on your gateway, if you really wanted to write 1/3 minus 1 and not even do the subtraction, you could do that and I'd be okay with it on the gateway. Okay? It'd be fine. I don't care. Don't have to simplify any kind of math kind of things. That's not a problem. But I think 1/3 minus 1 is okay, so we're just going to write it that way as negative 2/3 right now. How about x to the 1/5?
1/5 x minus 4/5.
Yeah, 1/5 x to the negative 4/5. Okay, is that all right? So here we would stop on a gateway. We could even kind of stop before this with it saying 1/5 minus 1 and 1/3 minus 1 if you want to. Especially if you think that under pressure you might accidentally just, have one of those moments that you just subtract something silly wrong. I don't want you to, because on a gateway, if you subtract something silly wrong, I'm going to count it wrong. I don't want to count it wrong, but I'm going to. So, all right. We don't get to stop this way in general, though. We want our problem to be like the problem looked originally. Well, the problem originally did not have negative exponents. It had radicals. So the fact first that they're negative means I need to stick them back in the denominator. But even after I do that, I won't be done. I need them back in radical form. Okay? So first, we put them in the denominator. So this is 3x to the 2/3. And if you can do it all in one step, that's fine. I don't care. I'm going to do it in 2 steps. 5x to the 4/5. Okay, so that's the first thing. I need the exponents to be positive. Once the exponents are positive, I can put them in radical form. They're a little bit messier than I started. What would x to the 2/3 look like in radical form?
X squared and then the cube root of that.
Yeah, very good as well. So x squared underneath a cube root. Is that okay with everybody? All right. How about x to the 4/5?
X to the 4th, or
Okay.
4th power underneath
Yeah. The 5th root, yeah. X to the 4th power underneath the 5th root. Nobody said they're going to look fun when they're done. However, it is valuable for me to make mention of the fact that nobody needs you to rationalize these. That's not necessary. And I mentioned this last time, but I'll mention it again. If you've got a radical with a variable underneath it in the denominator, that's perfectly fine. It's when you have a radical with a constant that we worry about rationalizing. Okay? So radicals with variables underneath them are perfectly fine to be left where they are. Okay, any questions on that? Okay, we're going to take this one step further. The directions are going to change slightly. We're actually going to find the slope on this next couple of them. It says find the slope of the graph of the function at the given point. It says use the derivative feature of the graphing utility to confirm your results. Not you results, my type. I've got a typo on paper too. Your results. Okay. So what we're going to do is we're going to start out much like we did before. We're going to take the derivative. Okay, but this one's by comparison to what we were just doing. Much cleaner. What's the derivative of 3x cubed? 9x squared. Is that part okay? What's the derivative of the minus 10? Yeah, it's 0. So write it or don't write it. Doesn't really matter at this point. I'm actually also going to put this as y prime of x because I want to show you something in a moment. So this is y prime of x equals 9x squared. So in order to do this second part where it says find the actual slope, what it's telling us that we're going to do is we're going to plug in this number x into x.
The period of this is pi over x.
So I have y prime of 2 equals, and then I have 9 times 2 squared. I know you know this, but it's easy to have one of those moments again too and remind yourself that the squaring happens before the multiplying, right? So we definitely want to do the 2 squared first. So 2 squared and then times 9, and that will give me what? 36. Grab your calculator. I want to show you how you can confirm this with your calculator because this is a very cool feature that you're going to want to utilize. There's 2 different operating systems, so I don't have a way to display this very well for them, but I'll draw them on the screen. And y equals, I want you to put the equation that they gave you to start with, 3x cubed minus 10. So y1 equals 3x cubed minus 10. Once you've done that, go back to the regular screen where you can do the adding and subtracting and all the things. Okay? So this, whoops, it's supposed to be a highlighter. This goes into y1. And then in your regular screen, you're going to hit the math button. And you're going to select option number 8. And option number 8 actually is called the in-deriv feature. Okay, did everybody find that? And you pressed enter on top of it, or you pressed the number 8. So there's 2 operating system possibilities. So if what I'm writing for you next is not what yours says, just hold tight and I'll show you what yours says. If you have an older operating system, which I do, it will actually say in-deriv right now on your screen with a parenthesis. Whose calculator says that? Literally none of yours. Seriously? Okay, for the purposes of if somebody's looking at this later and theirs does, I'm going to show you what it does. You're going to tell it y1, comma x, and comma the number 2 that you put in. So it will spit out 36 when you do it. All right, so I'm going to borrow yours, Daniel.
Mine's dead.
Yours is dead. I'm not going to borrow yours. All right, Brock. Okay, if yours looks like this, which sounds like it's everybody else at this point, and it has this like dotted like box here, and then this a line, and it has another dotted box here. It also has a solid box here, and it equals. Okay, does that look like everybody else's? Yours looks like that? Great. It's the same thing as what I already wrote down. You just need to know what to put where. This piece at the beginning, you're going to put X, and you know where your X button is, so that's fine. And inside of this dotted box, you want to put the function. Now, you can type in x cubed minus 10 if you wish. That's not a problem. But you could also just tell it y1. And if you don't know where you get the y1, I can show you. You hit vars. And then you choose yvars. And then you choose function. I think it's F and C. And then you choose y1. That's how you get it. But you can also type in x cubed minus 10 if you wish. So you hit vars, yvars, function y1. And then the last thing you do is you put this number 2, whatever your value is you're looking at, in that little box there. And what your calculator is doing is that same operation. It's doing it with a numerical method. It's not necessarily doing it with calculus techniques. So sometimes it might actually spit out to you something that looks a little funny. For example, your calculator might here say 35.9999999, and it's up to you to realize they meant 36, okay? So sometimes it will numerically approximate and actually be off by a tiny bit. But did anybody not get 36 when they did that?
What was the y one? Was it the 3x equals?
Yeah, at the top. Y1 is the original equation.
Oh, I thought, never mind. I thought,
That's okay. Any other questions? Okay, we're going to do one more of these. So this one says, find the slope of the graph. The function is the same directions we had before. Confirm with your graphing device, right? So forth. So we're going to do f prime, and now our variable is theta. Okay, so we have the 4 that comes along for the ride. What's the derivative of sine of theta? Just cosine, and it's positive, so I can just write 4 cosine theta. Now, I know that it feels really funny to have that minus theta at the end, but it's like having minus x. Okay, it's just the variable. So what's the coefficient of theta in this case? It's a 1. So this is like having 1x at the end, just like we saw earlier. The derivative of 1x is 1. The derivative of 1 theta is 1. And we have the subtraction sign before it. So I end up with minus 1 here. Trig functions are awfully nice because they usually mean there's very little cleanup. So those of you who are like hating on trig, you can like it for that purpose right now anyway. Okay. This is the derivative. But now we're going to evaluate it at 0. So we're going to find f prime of 0. So that's 4 cosine of 0 minus 1. You can let your calculator do it. Cosine of 0 is actually the value of 1 if you've got some of that unit circle stuff in your head. So I have 4 times 1 minus 1, which gives me 3. You can confirm this by putting the original equation into y1, and we can do that math 8 button. Okay, so underneath math 8, all of you have ones that showed up like this. I'm not going to put all the boxes anymore, but we'll fill it in as though we did. Oops. So we put an x right here. We put y1 right here, which is vars, y vars function y1. And in this case, we put a 0 down here because my x value is 0. And it should pop out with an answer for you that says 3. Did it do that? Okay, so here's what we're going to do. You have a reprieve because it didn't finish. We will finish this page on Wednesday, and we will move on to section 2.3. We will do our quiz on Friday instead of on Wednesday since we did not quite get finished. And I'll push the WebAssign homework to be pushed as well. At some point, and I don't know if it'll necessarily be Friday, but at some point you're going to end up with doubled up homework on your WebAssign. So my strongest recommendation right now is to do as much of the WebAssign as you can, even though it's not due till Friday. Because otherwise, what will probably happen between Wednesday and Friday, or at least likely, is that you have 2 assignments to do. And that might be a little more challenging. Have a great evening.